Hey everybody, so for today's lab, we'll be talking about the spectra. Let's go ahead and get so purpose for the lab. In this lab, students will learn about spectra, spectroscopy, and techniques that astronomers use to analyze spectroscopic data from celestial objects. Students will be provided with real SDSS spectra data from different stars and will learn how to identify hydrogen absorption lines on it, its meaning, and to calculate the hydrogen alpha strength. SDSS stands for the Sloan Digital Sky Survey. A bit of background. The basic model of the atom tells us that it has two components. The first is the nucleus, the central core of the atom, which is composed of protons that are positively charged and of neutrons that are neutral or have no charge. The second component is the cloud of negatively charged electrons which surrounds the nucleus. Each atom has a specific number of protons. For example, hydrogen, or chemical symbol H, has 1 proton, carbon has 6 protons, and calcium has 20 protons. An electron can orbit the nucleus of an atom only at specific distances known as permitted orbits. The number of protons in the nucleus determines the arrangement of these orbits that are found in different energy levels or shells. When an atom is excited, specifically when it absorbs energy, electrons change their energy levels to higher ones. When electrons from higher energy levels drop back down to lower energy levels, energy is released in the form of light. The frequency of the emitted light depends directly on the energy between the higher and the lower energy levels, and this determines the color of the light. Since the energy levels of each type of atom are unique, the photons an atom emits during this process have unique energies or colors. Every element has a unique spectrum of light composed of a set number of different frequencies, called lines spectrum. If the atoms of material are excited, given some energy, for example, by heating, the electrical composition can be determined by resolving those unique spectra from the emitted light. Here we see the hydrogen emission spectra, so we see the hydrogen lines of the spectrum. Spectroscopy is a technique of splitting light, or more precisely electromagnetic radiation, into its constituent wavelengths, a spectrum, in which much the same way that a prism splits light into a rainbow of colors. A scientist by the name of Gustav Kirchhoff identified through experiments 3 different types of spectra that chemicals emitted as he burned them in his lab. The 3 types of spectra that Kirchhoff observed are called the continuous spectra, the emission spectra or bright line spectra, and the absorption spectra or dark line spectra. And we'll see a picture of that coming right up. So I might be in the way of this, so I'm going to go ahead and make sure that I get out of the way. Let's see if I can get out of the way. So here we have one source of the of continuous light spectra, and what that looks like is, as you see, the continuous spectrum. It's all the colors blended from one to the next. Now, if the light passes through some cloud of gas, then we end up with 2 types of spectra. One, which is the emission spectra. So the cloud of gas gets its energy from the light source itself, and it in the relaxation process, where the energy levels of the outer electrons or in the outer shells drops down, it emits these specific lines, and that's why they call the emission spectra the bright line spectra. And the cloud of gas, if you can imagine, the light is going through that cloud of gas. The energy that is being absorbed during that process is then omitted from the continuous spectra. And that's the one that they call the dark line spectra, which in this case here we see it as the as the absorption spectra, right? And so it's pretty neat. The emission spectra, this is the type of spectra which occurs when electrons from low pressure gas absorb radiation. Specifically, we're talking about light, and re-emit in the form of photons at different wavelengths. The continuous spectra are produced by an object that gives off light at all wavelengths. And the absorption spectra, this occurs when a cold gas is between the observer and a source of continuous light. The gas absorbs the light that has the correct energies to boost its electrons to its various energy levels. Stars produce absorption spectra, except the very, very hot ones or very, very dense ones. The surface of the star is thinner than the gas underneath. The light from a hot, dense gas inside a star will produce a continuous spectra, and the cooler gas above it will absorb specific wavelengths of light, which appears as gaps in the underlying continuous spectrum. So what exactly does that look like? Well, we have a graph. And again, I will make sure that I get out of the way so you can see. So here we have the spectra of something. Here it says modern spectra are usually recorded digitally and represented as plots of intensity versus wavelength. And you can see there are these dips that are in the lines of the intensities that match up with the dark bands that are in what would be the continuous spectra. In this case, since we have the dark bands, right, these are absorption spectra. And there you'll see the H referring to hydrogen, and there are different lines for hydrogen. So from on the furthest right, we have the one that's called hydrogen alpha. In the center, we have hydrogen beta, and on the left, we have hydrogen gamma. The ones that we'll be looking at for this lab are hydrogen alpha. The easiest way to measure a star's temperature is precisely by observing the absorption lines of hydrogen in the visible part of the spectrum. And these are called the Balmer series. The strength of the Balmer series the strength of the Balmer series, or the Balmer lines of hydrogen that were being used to classify stars, correlated perfectly with the surface temperatures of the stars. So that as you go from cool stars to hot stars, you change the type of spectral lines that you observe because the atoms are in different states. So here we have the Balmer lines. We have it's from left to right. We have delta, gamma, beta, and alpha. And they all start with the H because we said that these were all hydrogen atoms. So it's hydrogen delta, then hydrogen gamma, then hydrogen beta, and lastly, hydrogen alpha. And that is all for today's presentation. If you have any, make sure that you just go ahead and reach out, contact me, and I'll get back to you as always as soon as I can. All right, take care. Good luck.